Imagine standing at the edge of a bridge that shouldn't exist. One end rests here, in the orbit of our moon. The other stretches impossibly across 4.5 billion kilometers to Neptune's cold realm. Not a bridge of metal or stone, but a tunnel carved through the very fabric of space and time itself. A wormhole, a shortcut through the cosmos. This is the dream we've carried since we first looked up at the stars and felt them pulling at something deep within us. The dream of reaching distant worlds, not in lifetimes, but in heartbeats. Of stepping through a doorway and emerging light years away, as casually as walking from one room to another. But dreams, as beautiful as they are, must eventually meet reality. And reality, it turns out, has rules. Strange rules. Rules written in the language of gravity and geometry, of quantum foam and exotic energy. Rules that whisper both possibility and warning. Let us take a gentle journey together through the mathematics of the impossible, through tunnels that may exist only in equations, or perhaps, just perhaps, in the quiet depths of spacetime itself. Our story begins not with wormholes, but with a poet, Edgar Allan Poe, better known for Ravens and Telltale Hearts, published in 1848 what he considered his masterwork. He called it Eureka. Buried in its tangled prose was a statement that would prove oddly prophetic. Space and duration are one. Space and time, Poe insisted, were the same thing. He had no mathematics to support this, no experiments, just intuition. That mysterious faculty that sometimes allows artists to glimpse truths that scientists spend decades proving. And nearly a century later, a young patent clerk in Switzerland would make that intuition real. Albert Einstein gave us general relativity in 1915, and with it, a new way of seeing the universe. Space-time, he showed us, is not a rigid stage on which events unfold. It is dynamic, responsive, alive in its own way. Matter curves it, energy bends it, and that curvature, that gentle warping of the cosmic fabric, is what we experience as gravity. The physicist John Wheeler captured it perfectly. Matter tells space how to curve, and space tells matter how to move. It is a conversation, an endless dance between substance and geometry, and you are part of it, right now, as you breathe, as your heart beats. Gravitational waves from distant catastrophes wash over you, stretching and squeezing spacetime by amounts smaller than an atom's nucleus. You are being gently deformed by the universe's distant dramas, and you never even notice. But general relativity is more than a description of how things are. It is a machine. You feed it an arrangement of matter and energy, and it tells you what spacetime will do in response. It predicts, calculates, reveals. But here is the subtle truth that haunts every physicist who works with Einstein's equations. The machine doesn't care if your input is real. You could feed it the gravity of a metal rod 10,000 light years long. The equations would dutifully calculate the result. They would not pause to ask whether such a rod could exist, whether the materials were available, whether the structure would collapse under its own weight. The machine simply answers the question you asked. It is up to you to determine which answers describe our universe and which describe only the landscape of mathematical possibility. And buried in that landscape, hidden in the equations like treasure in an old map, are the wormholes. The first hint came in 1935 from Einstein himself and his assistant Nathan Rosen. They had been troubled by singularities, those points where the equations break down, where gravity becomes infinite, where mathematics itself seems to scream in protest. Black holes contain such singularities at their hearts, and neither Einstein nor Rosen liked them. So they asked a question. What if a path falling into a black hole didn't end at the singularity? What if it kept going? What geometry would allow it to emerge somewhere else? The equations gave them an answer. The path would form a bridge, an Einstein-Rosen bridge, as it came to be known, connecting two different regions of spacetime, a tunnel through the cosmic fabric. But this bridge was fragile. More than fragile. It was suicidal. Any attempt to pass through would trigger a catastrophic collapse. The tunnel would pinch closed faster than light could traverse it, trapping anything inside in a gravitational vice that would crush it out of existence. The wormhole would strangle itself and you along with it. For decades, this seemed to be the final word. Wormholes might exist in the mathematics, but they were death traps, useless for travel, beautiful impossibilities. Then came John Wheeler, a physicist with the energy of a child and the depth of a sage. He never stopped asking. And in examining the Einstein-Rosen bridges, he saw something others had missed. These weren't just mathematical curiosities. They were shortcuts through space-time. If you could stabilize them, protect them, keep them open, you could step through and emerge light years away. You could reach the stars. He gave them their modern name, wormholes. But Wheeler also understood the cruelty embedded in the equations. A wormhole connects a black hole to its time-reversed twin, a white hole. And white holes, as elegant as they appear in mathematics, cannot exist in our universe. A black hole is a gravitational well, a one-way membrane that traps everything that crosses its event horizon. Light cannot escape. Matter cannot return. Entropy increases, and the laws of thermodynamics smile in satisfaction. A white hole is the opposite. It expels everything, forbids entry, decreases entropy. And that last part is the problem. The universe does not permit entropy to decrease. Time's arrow points one way only. White holes are thermodynamically impossible. Even if some exotic process in the early universe, some strange quirk of the Big Bang's physics, could have created white holes and scattered them across spacetime, they couldn't last. They would be unstable, collapsing explosively as matter drawn by their gravity pressed against the anti-horizon, unable to enter, building up energies that would eventually tear the structure apart. So wormholes seemed dead again, a beautiful idea murdered by the universe's strict accounting of entropy and stability. But then came the science fiction writers. Carl Sagan was writing a novel called Contact. In it, humanity receives instructions from an alien civilization for building something that would allow interstellar travel. Sagan wanted it to be real physics, not fantasy. So he called his friend Kip Thorne, one of the world's experts on general relativity, and asked for help. Thorne took the question seriously. He wasn't trying to propose actual technology. This was more of a thought experiment, a teaching tool. But he wondered, could you make a wormhole that was stable and traversable? Could you hold one open long enough for something to pass through? He worked the equations backward. Instead of starting with matter and asking what spacetime would do, he started with the spacetime he wanted, a stable tunnel, and asked what kind of matter and energy would be required to create it. The machine of relativity gave its answer: negative mass. Not antimatter, which has positive mass but opposite charge. Negative mass. Matter that weighs less than nothing. A football that weighs minus 500 grams. A book whose mass is negative 2 kilograms. Negative mass doesn't attract. It repels. It pushes space-time apart instead of pulling it together. And that pressure, carefully arranged in a shell around the wormhole's throat, could hold it open, could keep the tunnel from collapsing, could inflate the entrance to sit outside the black hole's event horizon, making entry possible without doom. There is only one small problem. Negative mass doesn't exist. Decades of searching have found no trace of it, and its existence would break one of the most fundamental principles of physics, the conservation of momentum. If you kick the ball with negative mass, it would fly backward from your foot. If you dropped it, it would fall upward into the sky. The universe's most basic accounting system would collapse. So negative mass appears to be a dead end. But remember, Einstein taught us that mass and energy are two faces of the same coin. If exotic matter cannot exist, perhaps exotic energy could serve the same purpose. And here, surprisingly, quantum mechanics offers a whisper of hope. In Copenhagen, just after World War II, a young physicist named Hendrik Casimir was forced to participate in an odd experiment. His mentor, Niels Bohr, wanted to test something called the gunslinger effect, the idea that automatic responses are faster than intentional ones. So graduate students dressed as cowboys and had mock duels in the streets while Bohr timed them with a stopwatch. Casimir was more interested in particle physics than pretend gunfights, but perhaps that image, two people facing each other across a distance, tension building between them, stayed with him. Because later, working on quantum mechanics, he imagined two metal plates held close together with nothing between them. And the calculations revealed something remarkable. The plates would spontaneously move toward each other, as if pulled by an invisible force. This was no new fundamental force. It was an effect of quantum fields, those invisible presences that fill all of space and time, constantly vibrating, fizzing with virtual particles that appear and vanish too quickly to be seen. Between the plates, those vibrations are restricted. The energy inside is less than the energy outside, and that difference creates pressure. The Casimir effect, as it came to be called, is a manifestation of negative gravity. Not negative mass, but negative energy. And in the right configuration, negative energy can do what negative mass would do: hold open a wormhole. Picture it. The entrance would be a sphere, glowing not with its own light, but with light from the distant place it connects to. You could look through and see another galaxy, another part of the universe entirely. You could see stars that won't be visible from Earth for millions of years. You could wave to a friend on the other side. And if the tunnel were properly stabilized, if enough negative energy were carefully arranged to counteract the throat's natural tendency to collapse, you could step through. The journey would be gentle. No crushing gravity. No tidal forces tearing you apart. Just a strange warping of your view as the geometry of the tunnel bent light in unfamiliar ways. And then you would emerge, having crossed distances that light itself takes years to span, having arrived before the news of your departure. But here we encounter a problem even more profound than engineering: causality itself. Because wormholes aren't just shortcuts through space, they're shortcuts through time. Imagine you build a wormhole. You take one end and accelerate it to near light speed, then bring it back. Due to time dilation, the slowing of time for moving objects, that end of the wormhole has aged less than the stationary end. The two mouths are no longer synchronized in time. If you step through from the stationary end, you arrive at the accelerated end, not just somewhere else, but somewhen else, in the past, before you left. Stephen Hawking once threw a party for time travelers. He carefully noted the coordinates: 52 degrees 12 minutes 21 seconds north, 0 degrees 7 minutes 4.7 seconds east, and the time, 12 noon Universal Time on June 28th, 2009. He prepared champagne even. He waited. No one came. Only after the party was over did he send out the invitations. It was his experimental proof that time travel is impossible, or at least that no one from the future wanted to meet him badly enough to violate causality. The paradoxes multiply like rabbits. You build a time machine, travel back, and destroy it before you built it. But if you destroyed it, how did you travel back to destroy it? The universe seems to protest. Cause must precede effect. The past must stay fixed. Some physicists, like Igor Novikov, proposed that perhaps time travel is possible, but self-consistent. The universe only allows histories that don't contradict themselves. You throw a rock into a wormhole intending to hit your past self, but something always happens. The rock bounces off a wall, or you slip, or quantum randomness intervenes to ensure the past remains unchanged. The universe protects itself. Others, like Hawking, suggested what he called the chronology protection conjecture. Time travel is simply forbidden. Some laws of physics we haven't discovered yet prevents it. The universe is safe for historians. And still others invoke the many-world interpretation of quantum mechanics, where every possibility branches into its own universe. Perhaps when you travel back in time, you enter a different branch of reality. In that universe, Hawking's party was always attended. In ours, it never was. All historians exist, and wormholes simply let you move between them. But even setting aside time travel, even assuming we could somehow prevent causality violations, we face another challenge: the energy conditions. These are rules that physicists have developed to distinguish realistic solutions from mere mathematical artifacts. They say things like energy cannot travel faster than light. Local mass must always be positive. Gravity at small scales must always attract. The Casimir effect violates the weak energy condition, the rule that energy must be positive. But it does so only in a tiny region between the plates. Average over a larger volume and the total energy is positive. The universe's books balance. The question is whether we could ever violate these conditions at large scales. Could a sufficiently advanced civilization amplify the Casimir effect from the microscopic to the macroscopic? Could they reach into the quantum foam, that seething sea of virtual particles and temporary wormholes at the Planck scale, and pull out a submicroscopic tunnel, then carefully, delicately enlarge it to human proportions? The mathematics doesn't forbid it, but mathematics is generous. Reality is strict. In 2019, researchers found a way to create wormholes without exotic energy in a special two-dimensional universe, a simplified model of spacetime. But these wormholes were useless for travel. It took longer to go through them than to simply cross normal space. They were shortcuts that weren't short. Our universe has 3 dimensions of space, not 2. Perhaps the same limitations apply. Perhaps all stable wormholes are actually longer paths than the routes they supposedly shortcut. Perhaps the universe is teaching us something. There are no free passages through space-time. Distance must be earned. And yet, the dream persists. Not because we have evidence, but because the equations permit it. Because the machine of relativity, when asked the right questions in the right way, whispers, maybe. Wormholes remain playgrounds for theoretical physicists, places to test quantum gravity, to probe the limits of our understanding, to ask what happens when space-time is pushed to its most extreme configurations. Even if we never build one, even if they're forbidden by the laws we haven't discovered, they teach us about the universe's deep structure. They teach us that space-time is more than we thought, that geometry can be wild and strange, that the fabric of reality might have hidden dimensions, secret passages, possibilities we haven't begun to explore. And they remind us of something essential. The universe is under no obligation to make sense to us. It doesn't care about our intuitions, our hopes, our engineering dreams. It simply is, operating according to principles we're still learning to read. Perhaps one day, centuries from now, some civilization, maybe ours, maybe another, will find a way. They'll discover new physics that makes exotic energy plentiful. They'll learn to stabilize wormholes, to prevent causality violations, to open gateways between the stars. Or perhaps they'll discover that wormholes, while mathematically beautiful, are physically impossible. That the universe draws a line at shortcuts through spacetime. That the only way to reach distant stars is the slow way, with patience, with time, with the humble acceptance that some journeys cannot be rushed. Either way, we'll have learned something profound about the cosmos we inhabit. For now, we float in uncertainty. We have equations that permit wonders and experiments that find nothing. We have dreams that stretch across galaxies and realities that keep us bound to the patient crawl of light. But the search continues. In laboratories deep underground, in observatories scanning the skies, in the minds of physicists pushing mathematics to its limits, we keep asking, are there tunnels through the fabric? Are there shortcuts home? And the universe, in its infinite patience, continues to answer in the only language it knows: mathematics, beautiful, cryptic, ambiguous mathematics that offers possibilities without promises, doorways without destinations. So we stand at the edge of the bridge that might not exist, looking across impossible distances, wondering, dreaming, calculating. And somewhere in the quantum foam, in regions smaller than atoms, in durations briefer than thought, wormholes flicker into and out of existence, tiny, temporary, useless for travel, but real nonetheless. The universe has tunnels. It just hasn't told us yet whether we're allowed to use them.